New study reveals profound properties of a simple metal alloy from the Ornell website, link in the description below. Like and subscribe. Scientists have measured the highest toughness ever recorded of any material while investigating metallic alloy made of chromium, cobalt, and nickel. Not only is this metal extremely ductile, which in material science means highly malleable, and impressively strong, meaning it resists permanent deformation, its strength and ductility improve as it gets colder. This runs counter to most other materials in existence. The team, led by researchers from Lawrence Berkeley National Laboratory, or Berkeley Lab, and Oak Ridge National Laboratory, published a study describing their record-breaking findings in Science on December 2, 2022. When you design structural materials, you want them to be strong but also ductile and resistant to fracture, said project co-lead Izo George, the governor's chair for advanced alloy theory and development at Ornell and the University of Tennessee. Typically, it's a compromise between these properties, but this material is both, and instead of becoming brittle at low temperatures, it gets tougher. Chromium cobalt nickel is a subset of a class of metals called high-entropy alloys, or HEAs. All the alloys in use today contain a high proportion of one element with lower amounts of additional elements added, but HEAs are made of an equal mix of each constituent element. These balanced atomic recipes appear to bestow some of these materials with an extraordinarily high combination of strength and ductility when stressed, which together make up what is termed toughness. HEAs have been a hot area of research since they were first developed about 20 years ago, but the technology required to push the materials to their limits in extreme tests that was not available until recently. The toughness of this material near liquid helium temperatures, 20 Kelvin or minus 424 degrees Fahrenheit, is as high as 500 megapascals square root meters. In the same units, the toughness of a piece of silicon is 1. The aluminum airframe in passenger airplanes is about 35, and the toughness of some of the best steels is around 100. So 500 is a staggering number, said research co-leader Robert Ritchie, a senior faculty scientist in Berkeley Lab's Material Sciences Division and the Child Professor of Engineering at UC Berkeley. Ritchie and George began experimenting with chromium, cobalt, nickel, and another alloy that also contains manganese and iron, or chromium, manganese, iron, cobalt, nickel, nearly a decade ago. They created samples of the alloys, then lowered the material to liquid nitrogen temperatures, around 77 Kelvin or minus 321 degrees Fahrenheit, and discovered impressive strength and toughness. They immediately wanted to follow up their work with tests at liquid helium temperature ranges, but finding facilities that would enable stress testing of samples in such a cold environment and recruiting team members with the analytical tools and experience needed to analyze what happens in the material at the atomic level took the next 10 years. Thankfully, the results were worth the wait. Many solid substances, including metals, exist in a crystalline form characterized by repeating 3D atomic pattern, called a unit cell, that makes up a larger structure called a lattice. The material's strength and toughness, or lack thereof, come from physical properties of the lattice. No crystal is perfect, so the unit cells in a material will inevitably contain defects, a prominent example being dislocations, boundaries where undeformed lattice meets up with deformed lattice. When force is applied to the material, think, for example, of bending a metal spoon. The shape change is accomplished by the movement of dislocations through the lattice. The easier it is for the dislocations to move, the softer the material. But if the movement of the dislocations is blocked by obstacles in the form of lattice irregularities, then more force is required to make the atoms within the dislocation in the material become stronger. On the flip side, obstacles usually make the material more brittle or prone to cracking. Using neutron diffraction, electron backscatter diffraction, and transmission electron microscopy, Ritchie George and their colleagues at Berkeley Lab, the University of Bristol, Rutherford Appleton Laboratory, and the University of New South Wales examined the lattice structure of chromium, cobalt, nickel samples that had been fractured at room temperature and 20 Kelvin. For measuring strength and ductility, a pristine metal specimen is pulled until it fractured whereas for fracture toughness tests, a sharp crack is intentionally introduced into the sample before it is pulled, and the stress needed to grow the crack is then measured. The images and atomic maps generated from these techniques revealed that the alloy's toughness is due to a trio of dislocation obstacles that come into effect in a particular order when force is applied to the material. First, moving dislocations cause areas of the crystal to slide away from other areas that are on a parallel plane. This movement displaces layers of unit cells so that their pattern no longer matches up in the direction perpendicular to the slipping movement, causing a type of obstacle. Further force on the metal creates a phenomenon called nanotwinning, wherein areas of the lattice form a mirrored symmetry with a boundary in between. Finally, if forces continue to act on the material, the energy being put in the system changes the arrangement of the unit cells themselves, with the chromium cobalt nickel atoms switching from a face-centered cubic crystal to another arrangement known as hexagonal close packing. This sequence of atomic interactions ensures that the metal keeps flowing but also keeps meeting new resistance from obstacles far past the point that most materials snap from the strain. So as you are pulling it, the first mechanism starts, and then the second one starts, and then the third one starts, and then the fourth, explains Ritchie. Now a lot of people will say, well, we've seen nanotwinning in regular materials, we've seen slip in regular materials. That's true. There's nothing new about that, but it's the fact that they all occur in this magical sequence that gives us these really tremendous properties. The team's new findings, taken with other recent work on HEAs, may force the materials science community to reconsider long-held notions about how physical characteristics give rise to performance. It's amusing because metallurgists say that the structure of a material defines its properties, but the structure of nickel, cobalt, chromium is the simplest you can imagine. It's just grains, said Ritchie. However, when you deform it, the structure becomes very complicated, and this shift helps explain its exceptional resistance to fracture, added co-author Andrew Miner, director of the National Center for Electron Microscopy facility at the Molecular Foundry at Berkeley Lab and professor of materials science and engineering at UC Berkeley. We were able to visualize this unexpected transformation due to the development of fast electron detectors in our electron microscopes, which allowed us to discern between different types of crystals and quantify the defects inside of them at the resolution of a single nanometer, the width of just a few atoms, which, as it turns out, is about the size of the defect in deformed nickel-cobalt-chromium structure. The chromium-manganese-iron-cobalt-nickel alloy was also tested at 20 Kelvin and performed impressively, but it didn't achieve the same toughness as the simpler chromium-cobalt-nickel alloy. Now that the inner workings of chromium-cobalt-nickel alloy are better understood, it and other HEAs are one step closer to adoption for special applications. Though these materials are expensive to create, George foresees uses in situations where environmental extremes could destroy standard metallic alloys, such as in the frigid temperatures of deep space. He and his team at Cornell are also investigating how alloys made of more abundant and less expensive elements. There is a global shortage of cobalt and nickel due to their demand in the battery industry, could be coaxed into having similar properties. Though the progress is exciting, Ritchie warns that real-world use could still be a way off for good reason. When you're flying on an airplane, would you like to know that what saves you from falling 40,000 feet is an airframe alloy that was only developed a few months ago? Or would you want materials to be mature and well understood? That's why structural materials can take many years, even decades, to get into real use. This research was supported by the Department of Energy's Office of Science. The low-temperature mechanical testing and neutron diffraction were performed at the Engine X ISIS facility at the Rutherford Appleton Laboratory, led by first author Dong Lu. Microscopy was performed at the National Center for Electron Microscopy at Molecular Foundry, a Department of Energy's Office of Science user facility at Berkeley Lab. The other authors on this project were Qin Yu, Sarab Kabra, Ming Zheng, Xochim Paul, Forna Kreutzer, Roping Zhang, Madeline Payne, Flynn Walsh, Bernd Gludewitz, and Mark Osta. Founded in 1931 on the belief that the biggest scientific challenges are best addressed by teams, Lawrence Berkeley National Laboratory and its scientists have been recognized with 16 Nobel Prizes. Today, Berkeley Lab researchers develop sustainable energy and environmental solutions, create useful new materials, advance the frontiers of computing, and probe the mysteries of life, matter, and the universe. Scientists from around the world rely on the lab's facilities for their own discovery science. Berkeley Lab is a multi-program national laboratory managed by the University of California for the U.S. Department of Energy's Office of Science. UT Patil manages ORNL for the Department of Energy's Office of Science, the single largest supporter of basic research in the physical sciences in the United States. The Office of Science is working to address some of the most pressing challenges of our time. For more information, please visit energy.gov/science.